Welcome to this explainer, where we're going on the ultimate maker's journey. We're taking you all the way from a beginner's bare breadboard straight up to quad-core cloud architecture. So whether you're literally just starting to tinker around, or you're an advanced user looking to optimize a remote sensor array, the ecosystem we're exploring today scales perfectly with your ambitions. Let's dive right in.
Here's our roadmap for today. We'll be scaling up in complexity, starting with your very first starter kit, dodging those common beginner pitfalls, optimizing your power, connecting to the web, and then finally unlocking cutting-edge Python integrations on the newest hardware.
All right, Section 1, the maker's first steps. Let's unbox that potential.
39. Now, you might be wondering, what's so special about that number? Well, it actually represents the total items you'll find in a standard Arduino R3 development starter kit. It's really not just a box of parts. It's your gateway to a massive world of physical computing. When you crack open that box, you aren't just looking at random wires. You're looking at the raw materials for literally hundreds of different inventions. A starter kit is sheer potential in a box. You're armed with everything from your main development board to environmental DHD11 sensors for temperature and humidity, add in the ultrasonic sensors, stepper motors, servos, and, plenty of jumper wires. You've got exactly what you need to start actually interacting with the physical world. But hey, before we start deploying autonomous robots, we all have to pass the exact same rite of passage, right? Blinking an LED. It's the hello world of hardware. You just drop it into the breadboard, keeping in mind the polarity, of course, anode to the pin and cathode to ground. And you wire up a 220 ohm resistor to protect it, connect it to digital pin 11, and write your classic setup and loop functions. It's simple, sure, but it is absolutely the foundational step for everything that comes next.
Moving right along to Section 2, avoiding common beginner mistakes. Time to adopt that detective mindset.
Veteran maker Becky Stern hit the nail right on the head with this quote. It's incredibly tempting to jump straight into building, say, a complex quadcopter. But think about it. Quadcopters have GPS, inertial measurement units, accelerometers, gyroscopes, and variable speed motor controls. If you try to build the whole shebang at once, you're going to get overwhelmed. You have to honestly reflect on your current abilities and break those complex projects down into simpler individual systems first.
So what are the biggest traps beginners fall into? Well, beyond overcomplicating things, the absolute worst is assuming your wiring is correct without actually verifying it. When a circuit fails, and it will, grab your multimeter. Verify your power and ground lines. Hunt down that missing semicolon in your code. And please, never ignore the official language reference guides and community forums. They are absolute lifesavers when you're trying to figure out tricky commands.
Okay, Section 3, optimizing power and hardware. Code is bug-free, so let's cut the cord. Now, selecting the right board completely dictates your battery life, and the difference is staggering. Look at a standard Nano compared to the Nano 33 IoT. The IoT's sleep mode drops consumption to below 6 milliamps. And if you switch over to bare architectures like an ESP12 or an NRF 528040, you're pushing that drain down to literal fractions of a milliamp.
If you want a remote soil sensor to survive out there for years on just a couple of AA batteries, you have to obsess over the tiny details that drain power. I'm talking about taking pliers and physically ripping the power LEDs off your boards. You need to bypass those inefficient voltage regulators. Writing data to an SD card hogs a ton of current, so you must physically power down that card between writing cycles. Honestly, aggressive deep sleep modes are the only way to go.
Which brings us to Section 4, connecting to the cloud. Let's look at the IoT blueprint. Taking your project from an isolated circuit to a secure internet-controlled device is actually surprisingly streamlined using the IoT cloud platform. You just register your Wi-Fi board, create a project, define a cloud variable, and build a quick visual dashboard widget. The system auto-generates a sketch for you, so you just modify it, upload it, and boom, you're live.
The absolute magic behind all of this relies on cloud variables. They completely dictate how data moves around. For example, if you want a web page button to turn on a physical lamp on your desk, you'd create a read and write Boolean variable. The trick here is mastering update policies. A button needs to update on change for an instant reaction, whereas something like a temperature sensor should only update periodically to save your bandwidth.
And finally, Section 5, the next generation. Welcome to the Uno Q architecture. The Uno Q is an absolute beast. It's essentially two powerful brains working perfectly in tandem. On one side, the MCU,
which is a 32-bit ST microelectronics chip, handles all the gritty, real-world physical pin interactions. But then, on the other side, the MPU is a quad-core processor running Debian Linux to handle OS-level tasks, networking, and Python. A dedicated serial bridge seamlessly links them together, merging the physical world with a high-level Linux environment.
To really harness this dual brain power, the ecosystem introduces something called bricks inside the App Lab. Think of bricks like Lego pieces for your code. A brick is basically a Python package wrapped in a specific API, allowing you to drag and drop incredibly complex modules right into your project. We're talking things like a trained AI object detection model. With just a few clicks, you are literally bringing enterprise-level AI capabilities right down to a microcontroller.
For the advanced tinkers out there, this opens up some massive real-world applications. Picture this, you're building a balancing robot. You can tune your PID controllers live over the web. You can even simulate values entirely in software before you ever touch a soldering iron to an IMU or a motor shield. And because of that Linux core, you always retain the freedom to just SSHN and develop straight from the command line.
From mastering the basics of microamp power limits all the way to deploying actual AI models on a quad-core Linux hybrid board, this journey really proves how the ecosystem scales seamlessly, right alongside your wildest ambitions. The tools are all here, just waiting for you. So I'll leave you with this one exciting final thought. Now that you've got everything from basic resistors to AI bricks right at your fingertips, what are you going to build first?